Okay, so welcome you all. It's a pleasure to have this day here at IMPA. We are welcoming 4 recent fellows of us here at IMPA. And what better way to welcome them than to let them speak by themselves and to present what they're doing. So there are going to be 4 talks today. At the end, there will be more information after that. We're planning to have a dinner that's going to be in a place called Tradição Imperial in Botafogo at 7 o'clock. So there will be more details later, but if you plan to join us, it will be nice. It will be very nice. Okay, so first speaker today is Lucas Mioranci. He's going to talk on algebraic hyperbolicity and other research interests. Okay.
Hello, everyone. Good afternoon. Yeah, I think it's working. So first, I'd like to thank the organizers for organizing this event and thank IMPA for welcoming me as a postdoc here. So I arrived recently last month, and I'll be staying here as a postdoc for at least 1 year. So nice to meet you all, and I'll... So I'd like to use this talk to talk about broadly on my research interests, on things that I like to think about, problems that I like to work on in the future, or at least a direction I would like to go on. Some things that are open, some conjectures that are famous and that I'm interested on, and also stuff that I worked on, particularly on algebraic hyperbolicity. That's something I worked on during my PhD. So I divide this talk into 3 parts. First, motivating questions, a broad overview of questions that I want to think in the future, both on short and long term. Algebraic hyperbolicity is something that I've worked on my PhD. I'll give you some definitions, some progresses, some interesting questions, and then tell about my result. And if I have time, I can talk about further directions, stuff that are open, and other stuff around algebraic hyperbolicity that we will work with. Okay. So first, in a broad sense, I like to study the geometry of project varieties by understanding some invariants of them, like the positivity canonical bundle, genus, degree, and space of curves lying on my surface, or on my variety. So, for example, you can ask, what curves can lie on a variety? In case you have curves, what does the space of those curves look like? Can we compute dimension? Can we say if it's reducible or not? Can we understand the space of curves? Is it going to exist? One more specific case, I can take a very general or general hypersurface X in Pn, fix degree E for the curve and geometric genus G, and ask, what are the curves that X have of degree E and geometric genus G? Can I have for all of them? How does it depend on the geometry of X or the degree of X? So as I change or vary the degree of X, what's going to happen to the space of curves? Are they going to disappear? Are they going to exist? Are they going to increase? If the degree gets too large, can I expect the same kind of curves? Do they behave differently? So there's all this study where all those questions can ask about X, about the curves, and how those things relate to each other. What kind of information I can get about X from the curves, and vice versa. So that's a way to approach higher dimensional varieties, for example, by studying curves lying on them. So for example, if you think about rational curves, so genus 0, we know that if the degree is at most n, then X is funnel, the canonical is negative, and X is going to contain many rational curves. However, if I go to the other direction, I take higher degree, bigger than or equal to 2n minus 2, then X contains no rational curves at all, as you're going to see on algebraic hyperbolicity. So I can ask the same questions. What's happening here? What can I tell about the space of rational curves? What does it say for me about X? What is special about this high degree? Why do the curves stop appearing? What makes them not appear? And what can I take from this case? And of course, what if the degree is in the between? Can I have any kind of rational curves? Well, there's this famous conjecture by Guzman that says that if the degree is at least n plus 1. So if x is of general type, then the degrees of the curves should be bounded. So you cannot have any degrees for the curves. Well, we also have this conjecture by Guzman, Harris, and Starr that says that, well, if you take a hypersurface, general always, of degree at most this, so it still has rational curves, then it's going to have rational curves of degree e.
I don't understand the conjecture. Rational. Oh.
Rational curves of degree e, exactly when the degree is at least this. And this is nice because it gives us some range where the curves of each degree start showing up. So for example, if my degree is between 20 minus 3 and this first bound, then we expect x to have lines, but no conics, cubics, or higher degree curves. Well, for the next bound, between this and that, x contains lines, conics, but no higher degree curves.
When you say
And
general, do you mean general or very general?
for the conjecture, general, yeah. So yeah, so on. When d is between those two bounds, x is going to contain lines, conics, cubics, no quartics, and so on. Oops. So for line has recently been solved, and it's completely solved by some papers by Harris, Kosko, and Riddle. And they show exactly this bound, and they solve the problem. For conics, there is this paper by Abe where he finds a bound. It's still not the best bound, something like 7/5n. And he shows that for that bound, x has lines, conics, but not cubics. And I don't know of any other progress for higher degrees. So it's still open in the general case. And this inequality here, it comes actually from a naive dimension count of what should be the dimension of the space of degree E rational curves on X. So that's the naive count, which we believe that this should be the dimension of the space of those curves. And when the curves exist, we get the previous conjecture. And one example of this is Clemens' conjecture. So for example, if you pick n equals 4 and d equals 5, then that's always 0 and expect to have finitely many rational curves. And the mirror symmetry gives a prediction for what should be the number of those curves, since they're going to be finite. Okay?
On the previous slide, was the third result also that you have no other things, lines, conics?
I know of no reference for cubics, no, only for lines and conics, yes. And even for conics, like Abe's paper is for like last year, 2023 paper. So this is all very recent. Okay. All right, so that's just giving an example of questions that I like to think about and things that are of my interest. But now let's talk more specifically about algebraic hyperbolicity. I'll give you the definition, some important conjectures, some context, and then talk about my results. So let's start from the definition. I'm going to define, so X, complex projective variety, I'm going to say it's algebraically hyperbolic if for every integral curve C on X, it has to satisfy this inequality. So 2 times the geometric genus of C minus 2 is bigger than epsilon times the degree of the curve for a fixed positive epsilon and a fixed ample divisor H for X. So you can think of this as a uniform bound of the genus over the degree that works for every curve on X. If you plug genus 0, 1, you see that it cannot have any rational or elliptic curves. So algebraic hyperbolic varieties don't have rational or elliptic curves. And this property is very connected to the positivity of the canonical bundle, meaning that the higher the positivity is, the easier it is to show that something is algebraic hyperbolic. And the closest you get to the bound for hyperbolicity, the harder it gets. It gets substantially harder, actually. Okay, so I believe this definition is interesting by itself. I mean, it's a bound of the genus over the degree for every curve on X. But actually, this is an algebraic version of a broader definition that's called Brody hyperbolicity. So we define X to be Brody hyperbolic when it has no non-constant holomorphic maps from the complex plane to X. So algebraic hyperbolicity was defined by the MIE as an algebraic version of that, where I have more tools to work on. And the MIE conjecture that they should be equivalent. So algebraic is a consequence of Brody, but the converse is still a conjecture, it's still open. But I do hope that they're equivalent. Okay. And classifying hyperbolic varieties is in general a very difficult problem. It is still open for dimension 2 and above. There's no general result that classifies for all of them. The only completely solved case is for curves, so for dimension 1. In this case, X is going to be hyperbolic exactly when the genus is at least 2. And you can show this by using uniformization theorem. The covering of that is going to be an open disk, and the only map from C to the open disk is constant. All right, so why are we so interested in that, and how does this connect to other things? Well, there are a lot of important conjectures that expect hyperbolicity to describe or say important things about the arithmetic and geometry of very general type varieties. So for example, Lang's conjecture says that X contains only finitely many rational points over finite field extensions exactly when X is hyperbolic. So if you take the case of curves, that's a Mordell-Faltins theorem. So in this sense, you can think of hyperbolic as the higher dimensional version of a Mordell-Faltins. Well, on a more geometric side, Lang also conjectures, so this conjecture is also by Lang, that X is hyperbolic if and only if every subvariety of X, including X itself, is of general type. So in this sense, I think hyperbolicity as a very general type condition imposes much more positivity on the canonical bundle. And then there is Gingrich-Lang conjecture that says that, well, X may be not hyperbolic, it's just of general type. In this case, it's still hyperbolic in an open dense, meaning that there is some proper subvariety S containing all the maps from C to X. So it's going to be hyperbolic outside of S. There has been a lot of work around those conjectures. Recently, especially in those last two, by mathematicians like Brotbag, Verriel, Rousseau, Merker, Trapani, Voisin, Pazienza. And they have partial results, some progresses, but in general, those conjectures are still wildly open, even for dimension 2. Have no general solution that works for all varieties. So there are some partial progresses. And the reason is that it's usually very difficult to say if something is hyperbolic. If you just give me some random variety, I cannot tell if it is hyperbolic. It's just like doing by doing some computations. For example, only recently, we got results like this. So Brotbach in 2017 showed that X, a general surface IMPN of degree D, is hyperbolic if the degree is sufficiently large.
Wasn't this already proved by Merker, Deverio, and Rousseau previously? I think what he did it to considerably improve the bound.
Improve the bound?
Yeah.
So, okay, maybe.
Course here, it's person who 10 or 15 years old.
Oh, okay, all right. So
I may be wrong, I may be confusing something, but I think that they proved that.
maybe Brotbach would improve the bound. So, and let's see the references again. Yeah. But yeah, that's, okay, it's still very recent, I believe. Yeah, so the question is actually what should be the best bound for this D? So on this paper, I believe they show this, the bound they found is exponential again, which is still a little far from the best expected bound. So it's conjectured by Kobayashi since the 70s to be 2n minus 2. And the reason is quite simple. If you go 1 degree lower, 2n minus 3, then X has lines, and it cannot be hyperbolic. So that's the lowest we can go for the degree. So not so close for that bound. We still have exponential bound. And that's where algebraic hyperbolicity comes into play. We have much more tools on that case. and have been much more able to do advances on Kobayashi conjecture when we're dealing with algebraic hyperbolicity. So by a series of works by Shu, Clemens, Run, I in the 80s, Bazan, Patsens in the 90s, and more recently, Koskun, Rido, and Young in the 2019, 21, 22, they have almost completely classified algebraic hyperbolicity for very general degree D hypersurfaces in PN. The only case still open is when D is 6 and N is 4. So for the 6th threefold, that's the last case open.
So I just checked. Indeed, your work, what the value and these guys proved was that every entire term was algebraic degenerate.
Oh, okay. Yeah, I remember like seeing the Broadback paper, and he claims that he was proving that.
So sorry.
Okay, no way. Okay, so of course, after we are done or almost done with the PN case, people start trying to classify for other types of varieties. So recently, Haas and Newton started doing for toric surfaces, and then was later developed by, or extended the classification by Kuskin, Riddle, and Robbins. And Young did for hypersurfaces in PM cross PN, where almost all the cases are done, except for some cases in P3 cross P1. So that's where I joined the effort, and I tried to use more or less the same setup all those people worked on, and generalize the results for hypersurfaces, or very general hypersurfaces, in homogeneous varieties, not only in PN. So let's first use the Grassmannian as the first example, where notation is simpler. So say that X is a very general hypersurface of degree D in GKN, that's the Grassmannian of K-planes in the n-dimensional vector space. Then suppose the dimension of the Grassmannian is at least 4. Then I show if the degree is at least this, which is the dimension of the Grassmannian minus the canonical minus 2, then X is algebraic hyperbolic. And the dimension, sorry, if the degree is at most that, then X contains lines, so it's not algebraically hyperbolic. For example, if you have G24, then 6 above, it's hyperbolic, or algebraic hyperbolic. And 4 or less, it has lines, so it's not algebraic hyperbolic. And of course, you can ask about, what about 5? Well, short answer is I don't know, but I'd like to elaborate more on that soon. But let's first show my general setting and the complete result. So what I do is I consider A my homogeneous variety, and I suppose I have some embedding into a product of projective spaces P1, Pm, in a way that this embedding is projectively normal. I'm going to call Hi the pullback of the corresponding hyperplane section for a Pi, and I'm going to suppose the Picard group of A is generated by those Hi's. So I can write the canonical divisor of A like this, as a combination of the Hi's. And then I'm going to choose X to be a very general hypersurface of degrees D1, Dm, which is something of this class. Okay. Then my theorem says that the dimension of A is at least 4, and degrees Di's are greater than or equal to this for all I's, then X is algebraically hyperbolic. And if Di is less than or equal to this for at least one of the I's, then X has lines, so it's not algebraically hyperbolic. So if this setting sounds a little weird, you can just think of Grassmannian and the Plucker embedding. You have all those conditions. And then by checking these conditions and basically just plugging in the numbers, we can get those bounds for many other varieties, or homogeneous varieties. So like before, you can plug the numbers for Grassmannians and get this bound. You can take product of Grassmannians, embed the product of projective spaces, and get this bound for product of Grassmannians. You can do something similar for flag varieties, and also for orthogonal Grassmannians, symplectic Grassmannians, and you can also take products of all those things. So you can just like use this to get bounds for algebraic hyperbolicity. And well, it's just one short of what we should expect of the best bound to be or not be. So let's talk about this. What can I say about the case, about the middle case, right? Is that hyperbolic or not? Well, the answer is depends. If the dimension of A is 4, I have example where it's not hyperbolic. So if you take P2 cross P2, 4 is not going to be algebraic hyperbolic. We can show it has elliptic curves. For P4 is the last case open. But if you go one dimension above, for dimension 3, there are also counterexamples, like P3 cross P1 cross P1. It's going to depend on the relation of the degrees, so it's a little more complicated. But if you take dimension 5, Warren's work for Pn cross Pn show that this is enough for algebraic hyperbolicity. And this is a little different technique about some oscillation locus. That's something that I'm working on in the future. So my conjecture is that dimension 5 should be enough. And that if I have dimension 5 for A, I'm going to have algebraic hyperbolicity for this 1 degree lower bound. Okay. So let's talk about some other applications of those techniques and other cases people are thinking about. So my setup, I assume that A was homogeneous, but actually it works, or at least the initial setup, works when A has an open homogeneous dense subset. And by using this, Koskun, Rideau, and Hasse-Newton classified algebraic hyperbolicity for some very general hypersurfaces in other spaces, like those. Yes?
Should I same techniques for quiver varieties?
For quiver varieties, I haven't seen, maybe. I haven't seen for toric varieties. And so, so all those results are for surfaces. My question is, can we do more or less, not the same thing, but build on those works and show something on higher dimension? Can we take the blow up of linear subspaces and, well, apply the same kind of ideas on that? Can you find the degree on when it's algebraic hyperbolic? For complete intersections, it's still open as well. There is this result by, I believe, Einarvosen, where they show that if X is a complete general complete intersection of this degree, and you have this bound, then all supervarieties of X are of general type. So if you think about the Lang's conjecture at the beginning, we should expect this to be hyperbolic, and that's the conjecture. So if the degree is at least this, it's a better bound because the conjecture is a little more interesting. So we conjecture that if the bound is at least this, then actually be hyperbolic. I don't know of any work for complete intersections on algebraic hyperbolicity. I know there's also some works by, I believe, Rousseau and Verrier on the Brody hyperbolicity, where they show for some kinds of complete intersections. And okay, we can also do those definitions and ask the same questions for complements of hypersurfaces and for log pairs in general. So we have Kobayashi conjecture for complements. So a complement of degree at least this. Complement of a hypersurface of degree at least this is hyperbolic, meaning there is no map from C to that. We can also define, on an analogous way, algebraic hyperbolicity. And we have a very similar set of conjectures on this case. Well, maybe as a summary of what I said, we can conjecture the following to be equivalent. So take the A and D a log pair, so a complex, a projective variety, and D a normal crossing divisor. So I can conjecture, well, the complement to be hyperbolic is equivalent for the complement to be algebraic hyperbolic, or the complement to have finitely many integral points, or all the subvarieties of the complement to be of log general type. And also have Green-Griffith's length conjecture for log pairs. So take log pair such that this is big instead of just canonical. So there is some proper supervariety containing all the bad maps from C to my complement. Right? Thank you.